Swayam Prabha. Digital India. Educated India.
Good morning, everyone. Welcome to this introduction to electronics class. This is our fourth session or fourth class. As you know, we have been discussing diode circuits. Let me recapitulate whatever we discussed in the last class. We have mentioned diode models, and using those diode models we have done some example. The diode model I have mentioned is mostly three types, but let me go through it very briefly once more. In the first diode model we mentioned that the diode is ideal, so there is zero voltage drop across the diode, and there is almost no current passing through the diode when the diode is off. So diode can be assumed to be a switch where we have considered diode as off when diode is open circuit, okay, or when diode is on, then we consider this diode is short circuit, okay. So using that we have tried to solve this example 1, okay. Example 2 also, using the same assumption we have find out, and you see that when the diode is off, this entire voltage, input voltage, will be across the diode, right? So you see that in the second case also the same things will happen. When the diode is off, this entire voltage will be across this uh, diode, and we can, if we measure V out here, we will get V out equal to V in. So that is the section we are getting, where V out equal to V in when the diode is off, and when the diode is on, the current is passing through this, okay, and you can get the slope is R2 over R1 plus R2, because we are measuring voltage that time across the R2, okay. So this is what we have discussed. Then we move and assume that constant voltage model of the diode, and in case of constant voltage model, either when diode is off, that is one case, okay, and in another case we have assumed that diode is on, means so I am assuming this is the diode, okay, and when diode is on means the diode is replaced by a voltage source, which is V gamma, or sometime we can write VD on, okay, that is close to 0.7 volt in case of silicon diode. And using that assumption we can also solve the problems, and I have discussed example 3 and example 4 in the last class, using that assumption that diode can be replaced by V gamma or VD on when the diode is on, okay. And that way you see that breaking point is shifted up to here instead of origin. In the previous example, this breaking point is at the origin, whereas here the breaking point is shifted towards VD on. For V in equal to VD on, then only the diode will be on, right? So you see the breaking point is shifted here. I hope these examples are clear to you. Now we have also mentioned that if we can use graphical technique to find out the solution of a diode circuit, okay, and we have taken the help of load line, that is nothing but the KVL equation in the loop here mentioned, drawn on the left hand side, and from there we can find out load line, and this point, which is basically intersection of load line and this exponential diode characteristics, which is basically giving you the solution of the solution of this circuit. Okay, now then we move and discuss the model of the diode when we use small signals. Okay, a small AC signal rather, and we have found out RD, that is basically diffusion resistance of associated with the diode. Okay, so we can replace diode with a small signal resistance. Okay, and or also we can replace along with RD, there can be CD. Okay, so you see here I have written CD and included CD and RD both. CD is basically diffusion capacitance, so if the AC signal we are using of high frequency, then we have to take into account this diffusion capacitance. So these are what we have discussed in the last class. Now so now what we are trying to do, we are trying to cover some application of diode. One of the application we target will be rectifier. Okay, and then we'll discuss limiter and clamper. I will try to cover the rectifier part today. Now you see, this is a typical DC power supply. Okay, in a typical DC power supply, we often need DC power supply because most of our electronic gadgets require DC voltages, and whereas our line supply is AC supply. So what we need to do, we need to convert this AC signal, okay, into DC output. Okay, and we need a typical DC power supply system. So this typical DC power supply system contains rectifier. Just now I said that rectifier is one of the diode application we will cover in this course. So this rectifier, okay, apart from this rectifier block, there will be a block of filter and a block of voltage regulator. Okay, so these blocks we will discuss one by one. So let's start with the rectifier block. Now what is the purpose of the rectifier? The purpose of the rectifier is basically it converts the incoming AC signal from the transformer to other form of to other AC power source to form DC. Okay, it can either come from transformer or some other AC power source, but the purpose is to convert it to some form of DC. Okay, now here I have drawn a very simple rectifier circuit, which basically contains a diode, n junction diode, and a load resistor RL. Okay, I have a AC signal here V, which can be coming from a transformer. Okay, now this is often known as half wave rectifier. Now, why it is half wave rectifier we will discuss in a minute, but let me explain how this circuit works. You see that we mentioned that when diode is on, we can replace diode as the short circuit. Okay, when diode is on, we replace diode as short circuit, and when diode is off, then we replace the diode as open circuit. Okay, so we have used that diode model here. So you see, when Vin is in the positive half of the positive half here, then we can replace that circuit like this, where the diode is on, and so this entire V will be across this load RL. Okay, will be across this load RL. Now what about in the negative half of the signal? In the negative half of your Vin, obviously the diode will be off because diode will be reverse bias. Okay, so you see diode is off here, and so if I measure voltage across this load resistance RL, the voltage will be 0 because there is no current there is no current flowing through the circuit, whereas here on the left hand side in the positive half cycle there is current flowing through this circuit. Okay, so if I measure output across this load resistance RL, we will get this. Okay, so in the positive V in this portion, so the entire V in will be across that RL. So the voltage across RL, that is V out, will basically replicate your V in. What about here in the negative half cycle? In the negative half cycle there is no voltage across RL. Okay, so you see the output will be like this, whereas in the positive half cycle the entire V in will be at the output, and in the negative half cycle when the diode is off there is no current flowing through the circuit, so V out will be 0 volt, right? So this is, we can say, half wave rectifier, because in the output we are getting one half that is in the positive direction. Okay, so always we get output in the positive half of the input. Okay, so it is rectifying, and we are not getting any output when the input is in the negative half. So in one half we are getting output signal, so that is why it is half wave rectifier. Okay, the reason I am saying it is rectifier, because it is rectifying the input and we are not getting and there is no negative portion of the cycle at the output. Okay, so it is rectifying, right? Now what about if we think about diode is not an ideal diode, and if we replace diode with a VD on, okay, in that case there will be voltage drop across diode in the form of VD on. Okay, so one case is when the diode is off. Okay, in the other case there is a voltage drop across VD on, where that is when diode is on. And so what we can say that when we measure voltage across this RL, okay, we will get again the input voltage, but there is a voltage drop VD on across the diode. Okay, so rest of the voltage will be across RL. Okay, so if you measure so this will be your V out. Okay, so this difference of this is basically V gamma or VD on, right? So this difference of this black line is, I am representing this black line is basically your output voltage. Okay, that is across RL, that is voltage drop across RL, and that is VD on or V gamma less than that of input voltage, because there is a voltage drop of V gamma or VD on across the diode when the diode is on. Okay, now if I measure, if I plot diode voltage across diode, in that case this is the voltage across diode. Okay, so this is your V gamma. So in the positive half cycle, when the input voltage is more than V gamma or VD on, the diode is on. Okay, so so this much voltage will be across the diode. Okay, whereas when the diode is off, the entire voltage will be across the diode, because there is no current flowing through RL. I hope this part is clear to you. Now you see this input signal Vi is of alternate polarity. Okay, so the average value is 0, whereas the output signal is unidirectional, right? Output signal is unidirectional because output has only positive cycle or positive half of the cycle. Okay, thus input signal is basically rectified. That is what I have mentioned in the last slide. Okay, so the input signal is rectified, but produces lower DC level compared to what is it is doing during the ideal dial model, right? Because you see there is a voltage of V gamma or VD on drop across the diode. if we can measure, we can find out the DC component of the output waveform, and it is possible to show the DC component or average the output voltage across this RL or in this half wave rectifier is Vp over pi. How this Vp over pi is coming, I will show you in the next slide. But this is the average voltage across this RL, okay, or in the average voltage we will get this is the DC output voltage. Now this diode, the 2 points I would like to mention. When the diode is on, the current is flowing through the diode, right? So we have to make sure that diode can handle that peak current, okay, that we have to make sure. What is that peak current? Peak current will be Vi minus V gamma divided by RL. That's your peak current, right? Says these when Vi is reaching at the peak, that minus V gamma over RL is basically your peak current. So we have to make sure the diode can handle that maximum current, okay. And also when the diode is off, entire voltage will be across the diode. You see, entire reverse bias voltage will be across the diode because the diode is off and there is no current flowing through the circuit. So we have to make sure this is known as peak inverse voltage, or in short it is known as, abbreviated form is PIV. So diode should be able to sustain that reverse bias voltage, okay, that is known as peak inverse voltage. So if you buy a diode from the market, in the data sheet you will get you will see that they have mentioned peak current, okay, which is present in the diode, and also you will see that they have mentioned peak inverse voltage. So the diode should be able to handle this large current, and also the reverse voltage, reverse bias voltage will be which will be across the diode when it is in reverse bias. It should be lower than that of peak inverse voltage, okay. Now as I mentioned, in case of half wave rectifier, the Vout average is basically Vp over pi. It is very easy to calculate how I am getting this expression. We know that Vout equal to V in is equal to Vp sin omega t, right? V in is, or Vi is equal to Vp sin omega t, right? Now if we don't bother about the voltage across my diode, we can say that Vout will be also Vp sin omega t when it is between 0 and t by 2, okay, because you see this is my Vout, right? This is my Vout. So this is 0, this is t over 2, this is t, right? So 0 to t over 2, it is Vout is Vp sin omega t, okay, whereas between t by 2 to t it is basically 0. So I have written it is 0 for t by 2 over t, from t by 2 to t, whereas it is Vp sin omega t when it is between 0 and t over 2, okay. So to find out the Vout average, we can basically we can write this 1 over t 0 to t Vout t dt. So that's basically your average, Vout average, and you can just perform that integration and you will get the average Vout is Vp over pi, right? Now this, let's now talk about full wave rectifier, okay. So far we have gone through half wave rectifier. In case of full wave rectifier, you see this is a typical circuit of full wave rectifier where we have two diodes, D1 and D2, and it is our transformer, okay. Now this transformer we have a is center tap, okay. So this is a typical center tap transformer, unlike the half wave rectifier case where we use simple transformer. We don't have you see, we don't have center tap transformer, we have ordinary transformer. But in the case of full wave rectifier, we need center tap transformer to close this loop. So if we go through this circuit operation, when in the positive half, okay, in the positive half, this diode D1 is on. Okay, I'm just not considering V gamma or VD1 voltage drop. I'm just assuming that the D1 is D1 and D2 is ideal. So when it is in positive half, the diode is basically on. Okay, so if the diode is on, then the current will flow like this. Current will go through here, it will come back through this path, right? So this is when D1 is on, right? Now in the negative half cycle, uh, in the negative half cycle, in the negative half cycle, here of the input voltage, this D2 will be on, okay, because D1 will be then reverse bias. When D2 is on, the current will flow like this. I hope you can follow. So current will flow like this and it will come back to this center tap transformer, you see. So that is why center tap transformer is important, because it is basically closing the loop. Now you see, in both the positive and negative half, the current through RL is in the same direction. Okay, if you see this blue line and this green line, that is the direction of the current I am showing. Both in the positive half and negative half of the input, the current is flowing in the same direction of RL. That means, you see, in this case, if we plot the output voltage over time, you will get not only positive half. Okay, so this is our positive. Let me draw. So this is the positive half. Okay, portion when here when D1 is on. Okay, and in the negative portion, in the negative half of the input signal, in the negative half of the input signal, D2 is on. Okay, so here your D2 is on, right? So you see, and again from here D1 will be on and D2 will be on. In other words, in case of full wave rectifier, okay, both your positive half and negative half we will get at the output. Okay, but in both the halves, the output signal will be in the same direction, or in both the halves the output will get positive output. Okay, here it is possible to show the DC component of the output waveform is 2 Vp over pi. Vp is the peak input signal. Okay, so this is a full wave rectifier, simply because at the output we get both positive half and negative half of the input signal, but in the same direction. Okay, so in case of half wave rectifier, you see, you have seen that it is not very efficient because we are losing one half of the signal. But in case of full wave rectifier, it is not the case. We get both the halves at the output, right? But the disadvantage is we need center tap transformer. So if we need center tap transformer, that will be more expensive. Okay, and the center tap transformer is larger than that of the ordinary transformers. Okay, now if you then let's talk about bridge rectifier. Okay, so this is also a kind of full wave rectifier. Okay, in this case, in the case of bridge rectifier, you see there are 4 diodes. Okay, unlike the ordinary full wave rectifier where there are 2 diodes, in this particular case we have 4 diodes: D1, D2, D3 and D4. So let me explain the operation of this circuit to you. So in this case, So say in the positive half, okay, I have drawn here. So in the positive half, the say this is positive and this is negative, and you see the current is basically flowing like this, okay, and it will go like this and come back here. So in other words, in the positive half cycle, D1, okay, D1 and D2 will be on, okay. The current is, or the signal is flowing through D1, is going through this RL in this direction, okay, and then it is going through D2 and come back to here, okay. Now what about the negative half cycle? In the negative half cycle of the input, okay, uh, you see current will start from here, current will start from here, current will go through D4, okay, it is going through the load RL, going back, then it is going through D3, okay, and coming back here. So if you follow this blue color line, which is the path, current path in case of negative half cycle of the input, you see D3 and D4 is on in this case. In the negative half cycle, D3 and D4 is on. So through this D4, it is going through RL and coming back through D3, okay, to the transformer. Now you see, if you look at the current direction in the RL, you see in both positive half and negative half, current is in the same direction. That means again, although in the input we have positive half and negative half, in the output we will have always, we will have the signal in the positive half, okay. That means it is basically rectifying the signal, okay. In both the cases we will have in the output signal is in the positive half, okay. So the circuit is managed to rectify the input signal, right. But the point, a couple of points to be noted here. One is in this case, the bridge, in this case of bridge circuit, we don't need center tap transformer. Here no center tap is required, whereas in the previous case we need center tap to closing the loop, whereas here we don't need center tap transformer. You see, through these 4 diodes, I mean through the 2 diodes in one side, one half, and through the other 2 diodes in other half, the circuit loop is completed, okay. So we don't need any center tap transformer, right. So that is one advantage. So this transformer will be of a smaller size and will be less expensive, okay. Another point is the output voltage you get here will be Vp minus 2 Vd on, okay. This is your output voltage, simply because you see in each half the current is passing through 2 diodes, so there will be 2 Vd on voltage drop. So rest of the voltage will be across that resistor RL. And similarly, I have shown you this current, okay. You see there is 2 voltage drops here divided by this, it should be RL instead of R out, it should be RL. Anyway, RL is the load. So this divided by RL is basically your current. In other words, you will get Vp minus 2 Vd on at the output. Whereas if you look at the full wave rectified circuit, here each cycle the current is passing, the signal is passing through only one diode. So the VL or V, so the V out will be equal to Vp or V minus or Vn, Vi should be Vi minus Vd on, okay. Whereas here it should be Vi, right, not Vp. it should be Vi minus 2 Vd on, that is the voltage drop across 2 diode, or 2 V gamma, whichever way I have written 2 V gamma here. Okay. Now another point is, if you look carefully, in this case, in the reverse bias case, the voltage will drop will be across the two resistors, right? Voltage drop will be across the two two diodes. Voltage drop will be across the two diodes. Okay. So the PIV, peak inverse voltage of the diode, will be half in the case of bridge rectifier. In the full wave rectifier, the entire reverse bias voltage will be across one diode. Okay. Whereas in case of bridge rectifier, this is divided between the two diodes, right? So the peak inverse voltage requirement in case of bridge rectifier will be half than that of the full wave rectifier. Okay. I hope this part is clear to you. So now whatever we have discussed so far, if we look carefully, this block diagram, you see, this is my signal at the secondary terminal of the transformer. Okay. So after the rectifier, if it is half wave rectifier, then output will be like this. Okay. If it is full wave rectifier, then output will be like this. So here we are missing one half. We are getting, in case of full wave or in case of bridge rectifier. Okay, in case of bridge rectifier, we are getting both the halves, right? Now even then, the output is varying considerably, and it is not good enough to use this full wave or bridge rectifier output directly to your electronic gadgets. So we need a DC voltage, that can be given to the electronic gadgets. Okay. So what we have to do, we have to improve this rectified signal even further. So one way of doing that is to use a block diagram, use a circuit known as filter. Okay. So let's go to this filter circuit and see how it works. Okay. So that is basically our diode capacitor combination. Okay. If we use capacitor, we will see that after this rectifier circuit, we will see that the output of the rectifier circuit improves considerably. Okay. So this is my this part is my half wave rectifier, right? And what I have done, we have added a capacitor with this half wave rectifier. Okay. So if I use a capacitor, what will happen? This is my input signal. Okay. This red line, I mean, I am drawing this red line on top of so that is my input signal. Okay. So after rectification, I will get only one half, only those positive halves at the output, if it is a half wave rectifier, as it is a half wave rectifier. Now what I have done, I have added a capacitor at the output. So if I add a capacitor at the output, what will happen? This is the output waveform. So output will follow this. Okay. Because there is a voltage drop Vd on. So and after reaching here, the output will be straight like this. Okay. Right. in case of ideal capacitor, the output will be straight. Why it is so? Because you see, when the diode is on, okay, the current will flow through this diode and it will basically charge the capacitor. It will keep on charging the capacitor. Now once this peak point is crossed, okay, the input signal cross this peak point, what will happen? The diode will be reverse bias. Why the diode will be reverse bias? Because you see, this V in has charged this capacitor up to this voltage here, okay. So now if the input voltage reduces, then this VD on will not be maintained, because here this is my input voltage, okay, this is my input voltage. So up to this point, it will charge the capacitor, and beyond that point, the capacitor voltage will make this diode reverse bias, okay. Capacitor is charged to capacitor is charged through this diode, is charged to Vp minus Vd on, that is the peak voltage at which the capacitor will be charged. So now when this from Vp it goes down, the input signal, then this diode will be reverse biased, because you see the voltage here across this capacitor will be larger, okay, will become such that if this input voltage will reduce, this difference will not be Vd on, okay. The difference between input signal and the signal across the capacitor will not be Vd on. So the diode will be off, or the diode will be reverse bias, okay. Now if the diode will be reverse bias, this capacitor voltage across capacitor it has nowhere to go, because the circuit is then like this, okay. This is my V in, this is off, and this is the capacitor, which will then have the voltage Vp minus Vd on, okay. That is the capacitor voltage, and this voltage there is no way this voltage will go, okay, or capacitor will fail to discharge. So you see, we will have a fixed in case of ideal capacitor, we will have a fixed voltage output, V out. So that then you see there is considerable improvement in the output signal, right, if we use a capacitor at the output of the rectifier circuit, right. However, any real capacitor will have leakage path, so it will have a resistor associated with it, through which a parallel resistor, through which the capacitor will drive or leak its charge, okay. The charge leakage will take place. So also we often use resistive load. So what I have done in this circuit, I have added a resistive load RL here, that might be is the leakage resistance of the capacitor, or a separate resistive load I have connected. Now if you add a resistive load, you see the voltage across this output, voltage at the output is not flat, rather voltage, instead of having like this, what is I have shown in the top plot, the voltage decreases like this, okay. Output voltage decreases like this. Why it is so? Because in the positive half, up to this Vp, the capacitor is charged, okay. So capacitor will reach here up to voltage Vp minus Vd on, okay. So this is this part of the we can simplify the circuit like this. So there is a Vd on, and capacitor is charged by that input signal. Where about here you see the diode is off. So diode is off, and the capacitor will discharge through this load resistance RL, okay.
through this load resistance RL, capacitor will discharge. So because of that discharge, there is a decrease in the output voltage, because capacitor is not maintaining its charge, it is discharging through that load RL. Okay, and of course how much it will discharge, it depends on the RC time constant. Okay, depends on the RC time constant, this discharge will take place, right? So that is what I have written here again. So if the capacitor value is large, okay, so this decrease in output voltage will be lower, whereas if the capacitor is a small value, there is much more drop in the output, because you see there depends on RC time constant. Okay, if the C value is much lower, then you see there is lot of drop of the output voltage. Okay, so this RC time constant is very important. Large the capacitor will give smaller ripple at the output. What is ripple? Ripple is the variation. Ripple is basically variation in the output voltage, because we want output a flat DC voltage, right? So ripple is basically variation in the output voltage. And why this variation is occurring? If the variation is there, as I mentioned to you before, in case of half wave or full wave or bridge rectifier, okay, because there is change in the output signal. And also if we use a RC filter circuit, okay, or even if only you see there is a leakage path in the inherent leakage path in any real capacitor, okay, and this RC time constant will dictate how much decrease in the output voltage will take place. In other words, the output is varying, output is not flat, and that variation in the output is known as output voltage is known as ripple. Okay, we can find out a expression of ripple, okay, or ripple voltage. So that is what I said, the charging and discharging of the capacitor causes ripple voltage in the output, right? So this is basically your this is the amount of ripple you are getting at the output, you see, because that is the variation. Okay, so this is, I am showing a full wave rectifier, full wave or bridge rectifier output. Okay, this dotted line, dotted curve, whereas if I use a RC after this full wave or bridge rectifier, the waveform will be like this, right? It is charging the capacitor and then it is discharging, it is charging and then it is discharging through that load resistance. Okay, so this charging and discharging of the capacitor causes basically the ripple voltage. Okay, because then the output is varying. So larger the capacitor or larger this load resistance RL, the smaller will be the amount of, or lower will be the amount of the ripple voltage, or less will be the ripple content. Now what is the we can find an expression of this ripple voltage. Okay, let's write V out. Okay, V out will be Vm exponential minus T dash over tau. If T dash is this axis, this is the T dash, so we can write Vm is the peak, Vm is the maximum voltage at the output, Vm or Vp. Vm is Vmax, that is the maximum voltage at the output. So it will decrease according to the time constant Rc. So we can write in this portion where the capacitor is basically discharging, we can write V naught equal to Vm e to the power minus T dash over tau, that is T dash over Rc. You can put Rc is basically time constant. If you put if you carefully see R and C units, you will get that this product of R and C is basically an unit of time. Okay, so RC is the time constant, the smallest the output voltage. Okay, this is smallest output voltage, that is basically VL, that is the lowest. Okay, VL is the lowest and VM is the maximum output voltage. So VL can be written as let me remove that. So V naught is basically Vm exponential minus T dash by RC. Okay, now we can write VL, that is the smallest output voltage, that is your VL. Okay, so this VL level we can write VL equal to Vm e to the power minus T dash by RC. Okay, because this capital T dash is, if you look at this graph, T dash is this much. Okay, so that the time it takes to discharge before it will charge again. So we can write VL in the form of exponential minus capital T dash over RC, right? This capital T dash is the discharge time, right? So V ripple, that is the ripple voltage or the variation in the output voltage, is basically Vm minus VL. The ripple voltage can designate as VR. VR is equal to Vm minus VL, and if you just substitute VL, then you will get this. Now often that T dash, that is the this discharging time, okay, T dash usually should be much less than RC. Otherwise what will happen, the capacitor will be fully discharged, right, if this condition is not valid. So the RC time constant is much larger, so the capacitor will start charging again, okay, before it is discharged considerably, right? So we can use this condition, okay, and can approximate this exponential term. So it can be approximated as 1 minus T dash over RC, and I am just neglecting the higher order terms. Okay, neglecting the higher order terms because simply because T dash is much less than RC. Okay, so ripple voltage can be written this. Now this T dash will be nearly equal to TP. Okay, why I am saying that? Because you see, let me draw this. So this is the rectified signal, and the output, so say this is charging, this is discharging, this is charging again, this is discharging. Okay, so that is basically my T dash, right? Now if you increase your RC, because as we are saying RC is much greater than that of T dash, okay, then what will happen, that it will discharge less. Okay, it will discharge, so it will discharge less. Okay, here this is my R1 C1, and this bottom one is say because of this is say because of RC. Okay, so you see RC is less than that of R1 C1, so that is why it discharged less. Okay, so you see, if you assume this assumption, I mean, if you consider this assumption that TC RC much greater than T dash, we can approximate T dash, because this is my TP, that is the time period. Okay, so as if we increase RC time constant, then this T dash is almost equal to TP. You see, this is my T dash in case of in the previous case, and if we use R1 C1, then T dash is this. So it is basically moving towards TP. You see, if you increase your RC time constant, then this is basically moving towards TP. In other words, we can approximate in case of large RC time constant, we can approximate that T dash nearly equal to TP. Okay, so we have replaced this T dash equal to TP in the expression. For full wave rectifier, TP is basically one half of the signal period, right? Because the entire signal is, in case of full wave rectifier, is this. So this is my input time period is from here to here. Say that is the time period Ti. Okay, sorry. Whereas in case of full wave, this TP will be half of that signal period, right? That is obvious. So we can replace this TP. As use that input signal frequency, okay, and write TP as 1 by 2f, right? That is obvious because we are just writing in terms of frequency, and this 2 factor is coming because the time period of the rectified output is half that of the time period of input signal. So this is the final expression of your ripple voltage. Okay, and you see it depends on maximum input voltage, okay, or the peak voltage, and it reduces if we increase RC time constant, and of course it will reduce if we increase the frequency, because if we increase the frequency, the discharge time, the time it will get by the capacitor to discharge will be right. Now, so that ripple voltage we can mention a particular term which is known as ripple factor. Ripple factor is basically a measure of effectiveness of the rectifier circuit. How efficient is your rectifier circuit, and it is defined by VRRMS over VDC. Okay, that ripple factor. So it is basically designates how effective is your rectifier circuit. The more the ripple voltage, the more will be your ripple factor. Okay, so this ripple factor is basically, it is the ratio of the RMS value of AC component, ripple component at the output, that is VRRMS, that is the ripple RMS value of the ripple component at the output, to the DC component VDC at the output waveform. Okay, you remember in case of simple half wave rectifier, VDC we found out VP over pi. Okay, so VDC VRRMS over VDC is your ripple factor. Now this ripple factor, it is possible to show that in case of you can find out the ripple factors in case of half wave and full wave using this formula, and VRRMS is basically root over VRMS minus VRMS square root over minus VD square VDC square, and Vrms and can be written this, and so we can find out the ripple factor around 0.483 in case of full wave rectifier. Okay, and in case of bridge, in case of half wave rectifier, it is are equal to 1.21. Obviously, in case of half wave rectifier, the ripple factor will be more, because the amount of ripple voltage you see will be much more, because other half, the negative half, we are not getting at the output. Okay. However, this ripple factor of the full wave rectifier, the expression can be written like this, where we have your load resistance, you have your capacitance, okay, and F is the frequency of the input signal. So this is the ripple factor. So with this, we will close today's lecture. Let me summarize what we have learned today. We have learned that using diode models, we can design and analyze the diode circuits. Okay, we have started one of the application of diode, which is basically rectifier. We talked about three different kinds of rectifier: half wave rectifier, full wave rectifier, and bridge rectifier, and we have discussed their comparative performance, and we have seen that in case of bridge rectifier, we do not need center tap transformer, and also the PIV diode rating is half of that of the full wave rectifier, or even half wave rectifier. And in case of full wave rectifier, in case of bridge rectifier, we need 4 diodes, but in case of half wave rectifier, in case of full wave rectifier, we only need 2 diodes. Okay, so see, this rectifier part we have gone through. We have seen that after rectification, the signal is not entirely DC. So what we have done, we have so here the signal is not entirely DC, and we have a signal like this if it is a full wave or bridge rectifier. So what we have done, we can apply a filter circuit in the form of the capacitor and resistor to improve the circuit performance. And what we get much less ripple at the output here of the filter compared to if I measure ripple here. Okay, and this ripple voltage, this ripple amount can reduce if we have your RLC larger. Okay, so if we increase your RLC or if we increase our frequency of the input, then your ripple will reduce. Okay, so this part we have learned today. In the next class, we will cover regulator block, so that will basically cover this whole DC power supply thing, and also we will go through other 2 diode applications, that is limiter and clamper. Okay, so thank you very much.